we are discussing an important topic, what is called array synthesis. In the last lecture, we investigated the arrays whose radiation pattern is specified in terms of its nulls. We saw that there are applications where we would like to place some nulls in the specific directions to avoid the interference coming from those directions. So, if the radiation pattern is specified in terms of the nulls of the radiation pattern, then we can synthesize an array by using the circle diagram. That is what we essentially investigated in the last lecture. Today, we investigate one more interesting array, what is called the binomial array, and later on we will go to the general array synthesis. As we have seen, when the number of elements in an array increase, the number of nulls also increase in the radiation pattern. That means there are directions in which there is no radiation. Now, we increase the size of the array because we want to increase the directivity. As we have seen, as the size of the array increases, the beam width of the radiation pattern decreases, and consequently the directivity of the array increases. So, if we consider a uniform array, then by increasing the length of the array or by increasing number of elements in the array, we can increase the directivity, but at the same time we also get more nulls in the radiation pattern. There may be some applications where these nulls are undesirable. We do not want to increase the nulls in the radiation pattern, but at the same time we want to increase the directivity of the array. Precisely that is what is realized by an array, what is called the binomial array. The concept is very simple. Let us consider a 2-element array to start with, and as we have seen, the radiation pattern for this can be given in terms of the z which we defined in the as a complex parameter last time. So, this one is having amplitude 1 and this one also has, let us say, amplitude 1, and it has a phase psi. So, it is e to the power j psi, where psi is beta d cos of phi. So, the angle phi is measured from the axis of the array. So, this angle is phi. So, the array factor, as we saw last time, that is equal to mod of 1 plus e to the power j psi, which we wrote as 1 plus z, where z is e to the power j psi. So, we define this complex parameter z, which is equal to e to the power j psi. Now, for this array, we have a null when z is equal to -1. So, when this quantity goes to 0, we have nulls. So, for this array, the null correspond to z is equal to -1, that is e to the power j psi is equal to -1. So, whenever this condition is satisfied, you get the null in the radiation pattern. Now, if you want that the directivity of the array should be increased, but the nulls should not change in the radiation pattern, one of the simplest way is that if I consider this as a polynomial, and if I take nth power of this polynomial, then the nulls of the function will not be changed. You will have again the nulls which will correspond to z equal to -1, and by expanding this polynomial, then we will get n plus 1 terms which will represent an array. So, as we have seen in the last lecture, a polynomial in Z can represent an array, and an array can be considered as a polynomial. So, if I consider now an array factor which is 1 plus z to the power n, we get the new array factor which is 1 plus z to the power n. So, if I expand this now, this binomially, I will get this is 1 plus n C1 z plus n C2 z square plus and so on to plus n Cn z to the power n. So, as we discussed in the last lecture, if I take the coefficients of z, they essentially give me the current excitation. So, now this array factor corresponds to an array which have n plus 1 elements, because there are n plus 1 terms in this polynomial, and the excitation coefficient would correspond to NC1, NC2 up to NCn. So, if I consider an array of n plus 1 elements with the coefficient as 1 NC1, which is equal to n, NC2 which would be n into n minus 1 upon factorial 2 and so on till I go to the last element, which is the NCn, which is again equal to 1. If I have the current excitation which are given by this, then the radiation pattern for this array would have the nulls only which are given by z equal to minus 1. So, the nulls will not change, but the length of the array is increased now. There are n plus 1 elements in the array, and if I look at the current distribution, it will start from 1, that will be n, and then the current will increase up to the center of the array, and again it will decrease. So, you have a symmetric function for the current. So, essentially the current distribution, if I look at the array, it will look something like that, and this will give me the radiation pattern which will have the same nulls which would correspond to z equal to minus 1. We can look at this in a little different way from our basic analysis of the array. Then let us consider now a 3 element array which is having binomial coefficients. So, let us say we have 3 elements which are having 3 elements binomial array. So, this would correspond to essentially 1 plus z square, that is what the polynomial would be. So, the coefficient for this would correspond to 1, 2 and 1. These are the binomial coefficient for 1 plus z square. So, if I consider now a radiation pattern which would be given by 1 plus z square, null would correspond to z equal to minus 1, and expansion of this will give me 3 terms. So, you have a 3 element array and the binomial coefficients would be 1, 2 and 1. Now, let us say this distance between these elements is d and this is also d. What we can think is this array now is equivalent to having array which is current like this and a current like this. So, this element which is having current amplitude 2, I can say is sum of these 2 elements, 1 and another 1. So, this array of 3 elements I can think of as the 2 arrays, which is one array and this is another array. Now, up till now we have considered the radiation pattern of the individual element which is isotropic. Before we investigate this array, one can ask a question: if the array elements were not isotropic, if they had some intrinsic radiation pattern, how would the array analysis change? So, the question we are asking before we investigate this is, if we consider an array of n elements which are no more isotropic but have a radiation pattern which is given by the primary pattern which is given by f of theta phi. That means if I go to some direction theta and phi, now the fields will not be uniform because of the individual elements, they will be weighted by this function what we call as the primary pattern of the antenna element. So, this function we call as the primary pattern. Now, if I consider a direction which is phi with respect to the axis of the array, as we have taken in our analysis, let us say this angle is phi. The radiation now will not be proportional to simply I, but will also be proportional to what is this quantity f theta phi, which is the primary radiation pattern. So, now in a given direction, the radiation now is a superposition of the fields because of the individual elements weighted by the primary radiation pattern. So, if we consider that all the elements are identical, so they have their primary radiation patterns which are identical, all the radiations from different elements will be weighted by the same factor in a given direction. So, I can write down now the radiation pattern for this array, which will be, now let us say the currents are given by I1, I2, I3 and so on, and if the spacing between them is d, the elements, and if the progressive phase shift between the elements is delta, then we define this quantity psi, which is beta d cos phi plus delta, and the array pattern as we discussed is equal to I1 e to the power j 0 plus I2 e to the power j psi plus I3 e to the power j 2 psi plus and so on. Now, each of this radiation is now weighted by this quantity f of theta phi. So, earlier we had the field at a far away point which was proportional to only current, and the phase was coming because of the propagational delay as well as the progressive phase shift. Now, we say that the amplitude is going to be weighted by this quantity which is the primary radiation pattern. So, essentially each of this term is to be multiplied by f of theta phi. So, you multiply this by f of theta phi, f of theta phi and so on, which is nothing but saying that we have this pattern f of theta phi, which is multiplying the pattern I1 plus I2 e to the power j psi plus I3 e to the power j 2 psi plus and so on. Now, this quantity represents the radiation pattern which we would get assuming the elements to be isotropic. So, this quantity we simply call as the array factor, and this is the primary radiation pattern of your element. So, the total radiation pattern of an antenna array, that is equal to the primary radiation pattern multiplied by the array factor. So, even if we have the antenna elements which do not have isotropic radiation pattern, but the elements are identical, that means their primary radiation patterns are same, we can still treat the array to be isotropic element array, and whatever radiation pattern we get, that we call as the array factor, finally we multiply that array factor by the primary radiation pattern of the antenna element. So, the array analysis does not change. Whenever we have an array of non-isotropic elements, first we replace those elements by isotropic sources, find out the radiation pattern, what we call as array factor, and then that array factor we multiply by the primary radiation pattern of the antenna element, and we will get the total radiation pattern. Now, this concept, which is multiplication of the radiation pattern, that can be applied in variety of situations. It is possible that intrinsically the antenna element does not have a radiation pattern, it is isotropic, but I can combine some of the elements and I can treat that combination as a basic element, which will then have a radiation pattern, which I can call as a primary radiation pattern, and so on. Precisely that is what we will do in the analysis of this binomial array. So, here initially we have the elements which are isotropic elements, and now we are saying that we have a 3 element array which has a current distribution 1, 2 and 1, and then we said this is equivalent to saying that there are 2 elements here which are having the amplitudes 1 and 1. So, essentially we are considering now this 3 element array as a combination of 2 arrays of 2 elements. So, if this spacing is d, this spacing is d and this spacing is d. So, now we are saying that this is equivalent to the 2 arrays of 2 elements. So, these two combined together, now I can call another element which is effectively located at the center of these 2. I can call another element which is located at the center of these 2. But now this element is not isotropic, because now this element is representing combination of these 2 elements. So, initially these elements are isotropic radiators, but if I think of this as a combination of 2 arrays and I say this array is equivalent to this radiating element, then now this one is having a radiation pattern which is the radiation pattern of these 2 element array. So, initially the radiation patterns of they were isotropic like that, these are now isotropic combination of these 2. But when we come here, they are no more isotropic, they have a radiation pattern which will look something like that. So, in this case your phi of theta phi is equal to 1 because the radiation pattern is isotropic, whereas now in this case you have a pattern which is phi of f of phi. So, essentially what we can do is first we can find out the radiation pattern of these 2 elements which is f of phi, then you find out the radiation pattern of this, product of the 2 will give the radiation pattern which is the radiation pattern of this 3 element array. So, for this, since the spacing is d, we can write here this psi which is beta d cosine of phi. So, for these 2 elements when we combine, we have a primary radiation pattern f of phi which is the array factor for these 2 elements, that would be given as f of phi would be equal to 2 times cosine of psi by 2. Now, if we consider the 2 elements which are again separated by a distance d, the array factor for these 2 elements also is given by cosine of psi by 2 because d is same. So, the total radiation pattern is nothing but product of this with the radiation pattern of these 2 elements which is again cosine of psi by 2. So, the total pattern which we get for this binomial array that will be equal to the f of phi multiplied by the array factor which is equal to 2 times cosine of psi by 2 multiplied by again the array factor which is cosine of psi by 2. So, we get a radiation pattern which is 2 times cosine square of psi by 2. So, note here whatever were the nulls now in the radiation pattern, the nulls are not altered. The nulls correspond to again the nulls of the 2 element array, which are given by this quantity cosine of psi by 2 going to 0. So, we got a radiation pattern which is square of this, and this concept can be extended now to any number of elements. So, if you are having a binomial array of n elements, you can think of that as a combination of doublets. So, you can split this into a pairs of 2, and then we can combine them again together to find that the radiation pattern is simply nth power of the radiation pattern of the 2 element array. So, this array is an important array because it can increase the directivity of the array without increasing the number of nulls in the radiation pattern. Having understood this, now we can come to the general synthesis of the array. That is, if somebody specifies the radiation pattern, then we would like to know what are the excitation of the currents to realize that arbitrary radiation pattern. So, let us discuss now what is called the general array synthesis. Without losing generality, let us say we now have the antenna elements which are isotropic, and as you have seen, even if they are not isotropic, we can always multiply finally by the primary radiation pattern of the antenna. So, as far as the array analysis is concerned, we can treat the array element to be isotropic, and let us say there are 2n plus 1 elements in the array. So, we have number of elements which are 2n plus 1, and let us assume that these elements are excited with the currents which are having conjugate symmetry. So, let us say we have this center element, this one, for which the current is given by I0, and then we have the currents which are on this side, which is I1, I2 and so on up to In, and on this side you have the currents which will be I1 conjugate, I2 conjugate and so on up to In conjugate. So, we are assuming essentially that there is an array which is having odd number of elements, and there is a symmetry in the current distribution in the sense that the amplitude of the currents are symmetric and the phases of the currents are antisymmetric. So, if this phase is delta, this will be minus delta and so on. Now, this quantity is here I can write down in terms of real and imaginary part. So, explicitly we can say that current of, let us say, kth element, that is I of k, is given by a k plus j b k. We can now do the array analysis essentially on the lines similar to what we have done earlier. We consider a point which is very far away from the array in a direction, let us say phi. So, this is the axis of the array. Let us say this angle is phi, and let us say we measure now the distances from this reference element, which is the center element, which is having current I0. So, the distance between the elements is d, and we can define this quantity now psi, the array phase psi, which is equal to beta d into cosine phi, We are not considering here the progressive phase shift explicitly, because that can be absorbed into the phase of this current, because we are considering now these currents which are complex in nature. So, whatever progressive phase shift we want to put on the array, that can be absorbed into these complex currents. So, we can define therefore the array phase which is simply beta d into cosine of phi. Once we do this, then now we can write down the array factor for this by simply summing up the fields which are induced by the individual antennas. So, applying simply superposition, we can now write down the array factor, which is the current which is I0, for which we are considering as the difference element. So, the phase for this will be 0, then this will be having a phase which will correspond to this psi. So, I1 e to the power j psi, I2 e to the power 2 j psi, and so on, and same thing we can do for the thing on the other side. So, we can write here I 0 plus I1 e to the power j psi plus I2 e to the power j 2 psi plus up to the nth element on the right side, which is In e to the power j n psi, and then I take the element which are on this side. So, this will be I1 conjugate e to the power minus j psi, because this will be now lagging with respect to this element by phase psi. So, you get here plus I1 conjugate e to the power minus j psi plus I2 conjugate e to the power minus j 2 psi plus and so on till In conjugate e to the power minus j n psi. Now, we can combine the terms of this, and noting that this I1 e to the power j psi and I1 conjugate e to the power minus j psi, they are complex conjugate of each other. This array factor we can write as I0 plus I1 e to the power j psi plus I1 e to the power j psi conjugate. This gives me I1 conjugate e to the power minus j psi plus so on, and the last term would correspond to In e to the power j psi plus In e to the power j n psi conjugate. Now, this thing can be combined together. This is the quantity which is I1 e to the power j psi and the conjugate of that. So, this essentially gives the real part of this quantity, 2 times the real part of this. So, we can write down the array factor as I0 plus 2 times real part of I1 e to the power j psi plus 2 times real part of I2 e to the power j psi plus and so on, 2 times real part of In e to the power j n psi. Now, noting that this current Ik we can write in terms of its real and imaginary part as Ak plus jBk, we can substitute into this, and that gives the real part of I k e to the power j k psi, that is equal to real part of a k plus j b k e to the power j k psi. Now, if I take this I can expand as e to the power j k psi is equal to cosine of k psi plus j sine of k psi. So, from here we can get this quantity, a real part of I k e to the power j k psi, that is equal to real part of a k plus j b k into cosine of k psi plus j sine of k psi. So, that is equal to a k cosine of k psi minus b k sine of k psi. So, I can substitute now in this expression for the array factor. So, this quantity will be 2 times a 1 cosine of psi minus b 1 sine of psi and so on. So, you can write now the array factor for this, that is equal to I 0, and from this I 0 will be a 0 plus j b 0, and since we are saying there is a conjugate symmetry, the b 0 has to be identically 0. So, we get from this the expression as a 0 plus a 1 cos of psi minus b 1 sine of psi plus 2 times, there is a factor 2 here in this expression. So, 2 times this quantity plus 2 times a 2 cos of 2 psi plus minus b 2 sine of 2 psi plus and so on till you go to the last term, which is 2 times a n cosine of n psi minus b n sine of n psi. We can write down this term on cosine in one summation and sine in another. So, that will give me a 0 plus 2 times summation k is equal to 1 to n a k cosine of k psi minus 2 times k is equal to 1 to n b k sine of k psi. Now, this is nothing but the Fourier series of this quantity array factor. So, essentially the coefficient which you have here, which represent now the real and imaginary parts of the current excitation, they are nothing but the Fourier coefficients of the array factor, which is nothing but the radiation pattern of the antenna. Now, this relationship we had seen earlier in general relationship, which was the Fourier transform relationship between the current distribution and the radiation pattern. The same thing now, however, we are seeing in terms of now the discrete current distribution, and also since we are having a periodicity in psi, as we know that the radiation pattern is periodic over psi, we get, instead of Fourier transform, essentially we get a Fourier series in this case. So if we know the radiation pattern, which is the array factor, and if we Fourier expand it, then the coefficient of Fourier expansion essentially represent the complex current excitation of the elements. So as we know that the Fourier coefficients can be obtained essentially multiplying this thing by cosine of k psi and integrating over a period, essentially we can get these quantities ak and bk. So now what we see from here is that the radiation pattern essentially is given by the Fourier series expansion of this, and larger the number of coefficients in this Fourier series, better will be the approximation to the array factor. In fact, we can say that if we take the infinite terms in the Fourier series, then this array factor, which is periodic over psi, can be exactly represented. So what that means is that by increasing the number of elements in the array, we can increase the accuracy of the realization of a given radiation pattern. So now while designing the arrays, we can have two constraints. Either we can design an array which says that the desired radiation pattern should be realized within certain error. In that case, then we will take number of elements, increase the number of elements in the array, so that we get the error between the two which is less than the specified error. So in this situation, the error between the desired radiation pattern and the realized radiation pattern is specified, and there is no constraint on the number of elements. The other possibility could be that depending upon the physical situation, somebody may specify the number of elements and then say, okay, get the best possible radiation pattern from this which is close to the desired radiation pattern. So in that case, essentially we find out the radiation pattern which is closest to the desired radiation pattern in the least square sense. So essentially the Fourier expansion, when we do this, it gives the radiation pattern which is best fit to the desired radiation pattern in the least square sense. So precisely that's what essentially we do now when we design the arrays, that first we express the radiation pattern in terms of psi, then we Fourier expand that function of psi which is periodic over 2 pi, and then the coefficient of the Fourier series gives you the current distribution or the excitation of the antenna elements. Let us look at one problem and this will become a little more clear. So let us say we want to design an array of 5 elements, and the array is broadside in nature, and its radiation pattern is a sectorial radiation pattern with 60-degree sector angle. So let us consider a problem, design an array of 5 elements. Now as we have seen earlier, the spacing between the antenna elements should be equal to lambda by 2 if we do not want overlap of the range of psi. Also we have seen if the spacing was taken less than lambda by 2, then the range of psi is less than 2 pi, and then the full range of psi is not covered by the visible range, and therefore it is optimum to take the spacing between the antenna elements to be lambda by 2. So let us say we take in this case also the distance d is equal to lambda by 2, and let us say now the radiation pattern which we want to realize by this is a sectorial radiation pattern in broadside. So it is having an angle which is 60 degrees, this angle is 60 degrees. So, we are now looking for a radiation pattern which is uniform over an 60 degree sector around broadside and no radiation beyond this sector. In practice, you might find an application where you would like to eliminate a certain zone on the in the radiation region. For example, if you have a satellite and I want to put an antenna beam over a certain terrain and we do not want to create interference nearby regions, we would like to create a beam which is uniform over a certain sector and it should be 0 ideally beyond the range of that sector. So, we have a requirement where now the phi essentially from here to here is 0, phi here to phi going from here to here the radiation pattern is 0 and it is 1 over this sector. So, essentially the specification now is that your array factor or the radiation pattern is equal to 1 for phi less than pi by 3, greater than pi by 3, less than or equal to 2 pi by 3, and it should be 0 otherwise. So, we want to find out now the excitation of the antenna elements which would produce this radiation pattern. Now, as we have seen earlier, first we have to find out the radiation pattern in the psi domain. So, psi will be beta d cosine of phi, and since we are taking d as lambda by 2, this is 2 pi divided by lambda into lambda by 2 cosine of phi, which is pi cosine of phi. So, now the array factor in terms of psi, which is f of psi, will be equal to 1 for this range of phi, and if I substitute that in this, I get the values of psi minus pi by 2 to pi by 2. So, essentially now we are looking for a function radiation pattern which is a function of psi, which is 1 over a range of minus pi by 2 to plus pi by 2 and is 0 elsewhere. So, if I plot now the radiation pattern in psi domain, this is f of psi, this is pi by 2 plus minus pi by 2, 0, and this is pi, this is minus pi. So, as we mentioned, the periodicity is over 2 pi. So, the function which we want to Fourier expand is this function. Its value is 1 and it is 0 in this range, 0 in this range. Firstly, we will note for this that this function is symmetric as a function as psi. So, the coefficient bk's will be identically 0 for this expansion, and we will get a 0 which is 1 over 2 pi minus pi to pi, amplitude is unity, d psi that is equal to 1 upon 2, and we can get here this quantity ak that is equal to 1 upon 2 pi. Now, note here this function is 1 only from minus pi by 2 to plus pi by 2, that is why you get this quantity which is 1 over 2. Similarly, this one is from minus pi but this quantity is only 1 over minus pi by 2 to plus pi by 2. So, we can as well put the limits as minus pi by 2 to plus pi by 2 cosine of k psi d psi, that will be equal to 1 upon k pi sine of k pi by 2. And bk's are identically 0 because this function is a symmetric function in psi. So, essentially now we get the current coefficients for this, which would be a0, which is 1 upon 2. Then we have a1, which is, if I put k equal to 1 in this will be 1 upon pi. So, a1 will be 1 upon pi. a2 will be, when I put k equal to 2, this will become sine of pi, which is 0. So, a2 will be 0. a3 is equal to minus 1 upon 3 pi when I put k equal to 3, and so on. These are the coefficients which we essentially get. So, now if I look at the current excitation for this array, as we have seen, these are conjugately symmetrically excited. So, this quantity is 1 upon 2 is excitation. The A1 is having excitation of 1 upon pi, and since this quantity is coming real, in this case this also will be 1 upon pi, that the currents. Second quantity which corresponds to this element is 0, and since we are permitted to take 5 elements, we want to design an array which has 5 elements. Since this current is 0, we can take the next current. This current is 0, this element is not there, and for which the amplitude would be minus 1 upon 3 pi. So, it will be minus 1 upon 3 pi. Similarly, this current will be 0 and next current will be minus 1 upon 3 pi. So, the array essentially which we get, which is 5 element, will be this. This is one element, this is another element, this is another element, then this element and this element. So, though we started initially with an array which is uniform array, that spacing between the adjacent element was same, which was lambda by 2, in synthesis process we essentially end up into an array which is non-uniform, because this current is now 0. So, you may say that we have 5 elements, but the spacing between the elements is not same. This spacing is double of the spacing between these 2 elements. So, essentially now if we excite this array with these coefficients, then we can get a radiation pattern which will be the sectorial radiation pattern of this nature. So, essentially the array synthesis problem is a rather straightforward problem. Once the array pattern is specified in phi domain, and if we take the inter element spacing to be lambda by 2, then the visible range of psi is equal to 2 pi, which is the periodicity of psi. So, the steps involved now in the synthesis are as follows. First, you take the radiation pattern which is specified in the physical angle phi, convert this pattern, radiation pattern in phi, to the radiation pattern in psi, which is the array angle psi. So, you get now the function which is periodic over psi equal to plus minus pi. Then you find out the Fourier coefficients for this function, and the coefficient of the Fourier series essentially will give you the current distribution. So, by doing this and by increasing the number of elements to any arbitrary number, essentially one can realize the radiation pattern which could be as accurate as possible to the desired radiation pattern. So, as we mentioned, there are two possibilities. One is if the number of elements are specified, then we get a radiation pattern which is the best fit to the given radiation pattern. If the number of elements are not specified, but the error is specified, then one can get the number of elements which would be give the error between the desired and the synthesized radiation pattern less than the specified error. So, this essentially completes the discussion on the array analysis and synthesis. That is, if the antenna array is given to you, we can find out the radiation pattern, but in practice the problem is opposite, that somebody specifies the radiation pattern and we have to find the current distribution. So, array synthesis essentially provides you a formulation which can give you the excitation of the currents for a given radiation pattern.